Hey there. Today, we're diving into a topic I'm incredibly passionate about: complex analysis. It's often seen as this mysterious, advanced subject, but I promise you, once you see its core ideas, it feels like uncovering a secret, more elegant way to do calculus. So, we're calling this guide Secrets of Complex Analysis No One Told You because I want to give you that aha moment. We're going to break it down into three key secrets. By the end of this video, you will be able to do three main things. First, you'll be able to work comfortably with complex numbers in both their Cartesian and polar forms. Second, you'll be able to quickly determine if a complex function is differentiable using something called the Cauchy-Riemann equations. And third, and this is where the magic happens, you'll be able to use complex integration to solve seemingly impossible real-world integrals. Ready? Let's get started with the first secret: the power of complex numbers themselves. Okay, secret number one is about complex numbers. You might be familiar with them as z equals x plus I times y, where I is the square root of -1. But there's a powerful geometric interpretation that can simplify a lot of problems. Let's first make sure we're comfortable with this standard form. You'll learn how to represent and add these numbers. When we add two complex numbers, like z1 plus z2, we just add their real parts and their imaginary parts separately. It's really just adding two vectors. Subtracting works the same way. Now, the real secret is understanding the polar form. A complex number z can also be represented by its magnitude, or length, e, and the angle, or argument, theta, it makes with the positive x-axis. The formula that connects these forms, and is arguably the most beautiful formula in all of mathematics, is Euler's formula. It states that cosine theta plus I sine theta is equal to e to the power of I times theta. This means we can write any complex number z as r times e to the I theta. Why is this a secret? Because polar form makes multiplication, division, and exponents ridiculously easy, which are all things you'll be able to do by the end of this scene. All right, let's see how powerful this is. Our first example is z equals 1 minus I. We want to express it in polar form, r times e to the I theta. First, we find the magnitude r. We use the Pythagorean theorem. R equals the square root of 1 squared plus -1 squared, which gives us r equals the square root of 2. Next, we find the argument theta. A common mistake is to just use arctan of y over x. Arctan of -1 over 1 is negative pi over 4. However, it's safer to visualize the number on the complex plane. 1 minus I is in the fourth quadrant. The angle negative pi over 4 correctly points to that quadrant. Always check your quadrant. Theta must match the location of z in the complex plane. So, our number in polar form is the square root of 2 times e to the negative I pi over 4. See how quickly we converted that? That's the first step. Let's try a practice question. Pause the video and see if you can express z equals -2 minus 2i in polar form. And here's the solution. You should have found the magnitude r was 2 times the square root of 2. The argument theta should have been -3 pi over 4. If you used arctan, you would have gotten pi over 4, but that's in the first quadrant, while -2 minus 2i is in the third. Plotting the point on the plane is the best way to catch this. So, the final answer is 2 times the square root of 2 times e to the negative I 3 pi over 4. Great job if you got that right. Okay, let's look at a second example. Let's find the product of two complex numbers. z1 equals 2 plus 2e, and z2 equals 1 plus the square root of 3i. Of course, you could just multiply them out in Cartesian form, but that's messy. Let's use polar form. First, we convert z1. The magnitude r1 is 2 times the square root of 2, and the argument theta1 is pi over 4 since it's in the first quadrant. So z1 is 2 times the square root of 2 times e to the ipe over 4. Next, we convert z2. The magnitude r2 is the square root of 1 squared plus the square root of 3 squared, which is 2. The argument theta2 is pi over 3. So z2 is 2 times e to the I p over 3. Now for the magic. The rule for multiplying numbers in polar form is incredibly simple. You multiply the magnitudes and add the angles. That's it. Let's apply it. The new magnitude is 2 times the square root of 2 times 2, which is 4 times the square root of 2. The new argument is pi over 4 plus pi over 3, which is 7 pi over 12. So the product is 4 times the square root of 2 times e to the I7 pi over 12. So much cleaner than multiplying polynomials. Here's a practice question for you. What is the quotient z1 divided by z2? How do you think division works? The rule for division is divide the magnitudes and subtract the angles. So the magnitude becomes 2 times the square root of 2 divided by 2, which is the square root of 2. The angle becomes pi over 4 minus pi over 3, which is negative pi over 12. If you got the square root of 2 times e to the negative I pi over 12, you're on your way to mastering this. My third and final example for this section is a classic: how to find the 3 cube roots of 1. This problem is almost impossible to tackle without the polar form of complex numbers. The question is asking for all numbers z such that z cubed equals 1. Let's first write z and 1 in polar form. For z, we'll write it as r times e to the I theta. For the number 1, its magnitude is 1 and its angle is 0. But here's the key secret. The angle of any complex number is periodic with period 2 pi. So 1 is not just e to the I0, it's also e to the I2 pi, e to the I4 pi, e to the negative I2 pi, and so on. We can write this generally as e to the I2 pi k for any integer k. This is the most common pitfall in these problems. Forgetting the 2 pi k will only give you one solution. Now we can equate the two forms. R cubed times e to the I, 3 theta must equal e to the I2 pi k. This means the magnitudes must be equal, so r cubed equals 1, and the angles must be equal, so 3 theta equals 2 pi k. Solving for r and theta, we find the magnitude r must be 1. The argument theta can be 0, 2 pi over 3, 4 pi over 3, 2 pi, and so on. Now we plug in values for k to find our unique solutions. For k equals 0, we get z equals e to the I0, which is just 1. For k equals 1, we get e to the I2 pi over 3. And for k equals 2, we get e to the I4 pi over 3. If we try k equals 3, we get e to the I2 pi, which is back to our first solution. 1. So there are only 3 unique roots. These 3 roots are negative 1/2 plus I times the square root of 3 over 2, and negative 1/2 minus I times the square root of 3 over 2. Geometrically, they form an equilateral triangle on the complex plane. This visual is always true for the nth roots of any number. They are always evenly spaced points on a circle. For a practice question, try finding the 4 fourth roots of 16. Remember to include the 2 pi k and think about the geometry. We've seen that complex numbers make algebra much more beautiful. Now, for our second secret, complex functions are special. They behave differently from the functions you're used to in real calculus, in some profound ways. The first thing we need is a way to tell which complex functions have this superpower of differentiability. The tool we use for this is the Cauchy-Riemann equations. Let's say we have a complex function f of z, where z is x plus iy, and we can write the function itself as u of x and y plus I times v of x and y. So u is the real part and v is the imaginary part. For this function to be differentiable at a point, its real and imaginary parts must be in sync. The Cauchy-Riemann equations are the mathematical expression of this synchronization. There are 2 conditions. The first is that the partial derivative of u with respect to x must equal the partial derivative of v with respect to y. The second is that the partial derivative of u with respect to y must equal negative the partial derivative of v with respect to x. If both conditions hold in a region, then the function is differentiable in that region. A function that satisfies these equations in a region is called analytic or holomorphic. These are the special functions of complex analysis. Let's work through an example. Consider the function f of z equals the complex conjugate of z, which is x minus iy. The goal is to determine if this function is differentiable anywhere. First, we identify the real and imaginary parts. Here u of xy is x, and v of xy is negative y. Remember, the I is not part of the imaginary part v. v is the coefficient of I. Next, we find all four partial derivatives. The partial of u with respect to x is 1. The partial of v with respect to y is negative 1. The partial of u with respect to y is 0, and the partial of v with respect to x is 0. Now we check the Cauchy-Riemann equations. The first equation, uxx equal vy, becomes 1 equals negative 1. This is false. The first equation fails. The second equation, uy equal y, becomes 0 equals negative 0. This is true. Since the first equation is not satisfied, the function is not differentiable anywhere in the complex plane. It is not an analytic function. This is a crucial distinction from real analysis, where a function like this would be differentiable at every point. For our second example, let's test a function that is analytic. F of z equals z squared. Our intuition should tell us this one is differentiable. First, we need to split this into its real and imaginary parts, u and v. This requires a little bit of algebra. We expand zi squared. Remember, zi is x plus I of y. Squaring that gives us x squared plus 2i xy plus I squared y squared. Since I squared is negative 1, this simplifies to x squared minus y squared plus I times 2xy. So we have u equals x squared minus y squared and v equals 2xy. Next, we find all four partial derivatives. The partial of u with respect to x is 2x. The partial of v with respect to y is also 2x. The partial of u with respect to y is negative 2e. And the partial of v with respect to x is 2i. Now we check the Cauchy-Riemann equations. Here we must be very careful with the second equation, which has a minus sign. The first equation, ux equal vy, becomes 2x equals 2x, which is true for all x. The second equation, uy equals vx, becomes negative 2i equals negative 2y, which is true for all y. Since both equations hold for all points in the complex plane, f of z equals z squared is differentiable everywhere. We call this an entire function. For a practice question, try this one yourself. Is the function f of z equals the real part of z analytic? Let's quickly go through the answer. F of z equals x, so u is x and v is 0. Ux equal 1, vy equals 0. The first equation, 1 equals 0, is false. So f of z equals z is not analytic anywhere. This is another example of a function that's perfectly fine in real analysis but not differentiable in the complex plane. Okay, one last example for the Cauchy-Riemann equations. This one is a little trickier. Consider the function f of z equals the product of z and the conjugate of z. We might be tempted to say it's not analytic because we know z bar isn't. But let's work it out carefully. First, let's simplify the function. Times z bar is x plus I y times x minus iy. Using the difference of squares formula, this is x squared minus iy squared, which is x squared plus y squared. This is the magnitude squared of z. The real part u is x squared plus y squared, and the imaginary part v is 0. Now we take the partial derivatives. Ux is 2x, y is 0. Uy is 2i, and vx is 0. Now we check the equations. Here's where the secret lies. The first equation, 2x equals 0, is only true when x equals 0. The second equation, 2y equals 0, is only true when y equals 0. Unlike z bar, which was never differentiable, and z squared, which was differentiable everywhere, this function is only differentiable at a single point. The only point where both conditions are met is x equals 0 and y equals 0, which corresponds to the origin z equals 0. A function that is only differentiable at a single point is not considered analytic anywhere, as analyticity requires differentiability throughout a region. But it's a great example of this intermediate behavior. For practice, try to find where, if anywhere, the function f of z equals the imaginary part of z is differentiable. Let's work through it. F of z equals y, so u is y and v is 0. Ux equals 0, uy equals 1, vx equals 0, vy equals 0. The Cauchy-Riemann equations become 0 equals 0 and 1 equals 0. The second equation is always false. So f of z equals imz is not differentiable anywhere. By now, you should be a pro at this. Okay, hold on to your hats because we're about to unveil the third and arguably most incredible secret: the link between complex functions and real integrals. This is where it all comes together. The first major result is the Cauchy integral theorem. It states that if you have an analytic function, f of z, and you integrate it along a closed loop C that doesn't contain any problems with the function, the answer is always 0. This is a crazy powerful generalization of the fundamental theorem of calculus. It means the integral is path-independent inside a region where the function is analytic. It's an incredible shortcut. But what happens if the loop does contain a problem? What if it encloses a point, not, where the function is not analytic? This is where the magic happens, with the Cauchy integral formula. This formula says that the integral of f of z over z minus z naught is just 2pi times the value of the function at z naught. Notice, this works even though z naught makes the denominator 0. It's not a regular integral you could solve with real calculus. This seems disconnected from real integrals, right? Here's the final twist. This formula can be used to evaluate many tricky definite integrals of real functions. Let's see our first example. We're going to calculate this complex integral, the integral of 1 over z squared, along a circle of radius 1 centered at the origin. Our goal is to see if we can use the Cauchy integral formula. Let's compare our integral to the formula, the integral of f of z over z minus z naught. In our case, the function f of z is the constant 1. The point z naught would be 0. However, we have z squared in the denominator, not z minus 0. This is a different form of the formula, which requires differentiating. Here's the simpler way. This function f of z equals 1 over z squared is analytic everywhere except at z equals 0. The circle C of radius 1 centered at the origin does contain this problem point z equals 0, so the Cauchy integral theorem doesn't directly apply. But remember that an analytic function has an antiderivative. The integral of 1 over z squared is negative 1 over z. When we evaluate this antiderivative at the end and start points of a closed loop, the result is always 0. This is a bit of a trick. Although the singularity is inside the loop, the fact that its antiderivative exists makes the integral 0. This example shows that you need to be careful. Sometimes a singularity can be ignored if the function has a simple antiderivative. For a practice question, try evaluating the integral of 1 over z minus 2 cubed over the same circle C. For our second example, let's use the actual Cauchy integral formula to solve a complex integral. Let's find the integral of e to the z divided by z minus 1 around the same circle as C, where the magnitude of z is 2. Our goal is to apply the formula. Let's first identify the components. The function f of z is e to the z, which is analytic everywhere. The pole, or problem point, is at z equals 1. Now we need to check if the contour C encloses the pole z0. The circle C has a radius of 2, so it's a large circle that definitely goes around the point z equals 1. This means the Cauchy integral formula applies. Now we can just plug the values into the formula. The formula says the integral is 2pi times f at the pole, z0, which is 1. So we need to evaluate f of 1. Since f of z is e to the z, f of 1 is e to the power of 1, which is just e. And that's it. The answer is 2pi. We didn't have to parameterize the contour or do any messy real integration. We just used this powerful formula. Try this practice question. Calculate the integral of sin z divided by z minus pi around a circle of radius 4 centered at the origin. We've reached the final secret. This is where we bring the previous two together and use complex analysis to solve real integrals. Let's tackle the integral from negative infinity to infinity of sine x over x dx. This is a famous integral that you've probably seen. It doesn't have an elementary antiderivative, so you can't solve it with standard real calculus techniques. But we can solve it in a few elegant steps using complex analysis. We start by relating this to a complex integral using Euler's identity. The integral of sine x over x from 0 to infinity is exactly half of the integral of e to the I x minus 1, all divided by x from negative infinity to infinity. Now, the problem with the complex integral is that it has a singularity at x equals 0, where the denominator is 0. To handle this, we use a contour integration technique called a semicircular detour. We create a large semicircle in the upper half plane and a small semicircle around the singularity at the origin. The integral over the large semicircle goes to 0 as its radius goes to infinity. The integral over the small semicircle gives a contribution of p(e) times the residue at 0, which is the value of the function it's trying to circle around. The function is e to the iz, and at z0, e to the iz is 1. So the contribution is p I times 1, or pi. So the complex integral is equal to this contribution from the singularity, which is pi. We then take the imaginary part, which is pi. And since our original integral is half of this, the final answer is pi over 2. We've solved a tough real integral using a contour in the complex plane. For a much more challenging practice question, try to use contour integration to evaluate the integral from negative infinity to infinity of x squared over x squared plus 1 squared. So, we've come to the end of our journey. We've seen 3 incredible secrets that complex analysis holds. First, the power of complex numbers. The simple polar form z equals re to the I theta makes algebraic operations like multiplication, division, and finding roots incredibly elegant. It turns tedious calculations into simple geometric transformations. Second, the superpower of complex differentiability. The Cauchy-Riemann equations give us a simple test for which complex functions are special. These analytic functions have extraordinary properties that don't exist in real analysis. And third, the connection between the complex and real worlds. The Cauchy integral formula, born from the properties of analytic functions, gives us a tool to solve some of the most difficult real integrals, like the since function integral. We started by wanting to master these 3 ideas, and I hope now you feel more confident in them. This is just the tip of the iceberg in complex analysis, but these core secrets are what make the subject so profound and so useful across all branches of science and engineering. Thanks for watching. I hope you've enjoyed uncovering these secrets with me. Keep exploring.